Welcome to a 5-series pre-recorded lecture on capsule dosage form. In this series, I've decided to organize the lecture into 5 short videos for ease of assimilation and retention of the information. The very first recording in the playlist is the introduction to the dosage form. This recording is really tailored for pharmaceutical calculation module. However, students enrolled in dispensing year 3 for capsules or for year 2 for pharmaceutics 2A lab, feel free to use the resources. The primary lecture content is designed around pharmaceutical calculation, 16th edition, and the pages are shown on the slide. What are we going to look at? Interpretation of prescription or a formulation, looking at accurately calculating our ingredients, looking at different scenarios where the active ingredient could be a pure powder, a triturate that you may have to make, or tablets crushed and converted into what we call tablet powder. Now, at the core of capsule dosage form and charts is the interpretation of prescription or the medication order or reading of formula, measurement system, understanding milligrams, microgram, whatever it is that the dosage is written as, calculating doses, and this doesn't include any based on BMI or body weight, but those are foundation calculation you should be able to do to arrive at your dose, and importantly, pharmaceutical metrology, which is the act of measuring and weighing accurately. Now let's get into it. Some key terms, and there are 2 main methods for calculating for capsules compounding on a small scale: the displacement information, or what we call the fill weight, and the density of the powder and the volume of the shell. So those 2 scenarios can play out with your calculations. Now, what are capsules? Capsules are solid dosage forms generally used for oral administration. They are made up of hard gelatin capsules or soft gelatin capsules, encapsulating or enclosing one or more active ingredient, and we normally have fillers, what we call diluents or bulking agents, such as starch or lactose for the hard gelatin capsules. And here is a picture of the soft gel liquid fill inside, and we're focusing on the hard gel where powder is what is filled inside. So the soft gel capsules, as I said, it's a soft gelatin with like a liquid ingredient, whereas the hard gelatin is normally made up of a body and a cap. I'm going to show you a picture later on, and there are different sizes based on the dose that you're trying to encapsulate for the patient. And so as the size varies, so does the volume of the shell that varies. Now, compounding capsules can take place on a lab scale, whether in a clinic, a hospital setting, or your pharmacy. And the picture here is very intentional. The powder is placed on an ointment tile. It's formed into what we call a mound, which is like a rectangular cake in which the capsule body is punched and filled with powder. Bear in mind that the cap doesn't have powder, only the body is filled with powder, and the cap is snugly locked in place. Now, what we normally use is the density of the information, the density of the powder, and the volume of the shell, and hence you have calculation where you employ the equation density is equal to mass over volume. You can change the parameters to solve for any particular aspect that you want. The displacement value, we normally say capsules have a fill weight. So if you look at this picture right here, there is a filled amount of powder being filled in the body. When you snap on the cap and check the weight of that capsule, and of course you subtract the weight of the empty shell, you end up with what we call the fill weight. It's the amount of powder that is enclosed within the capsule. So whenever you see fill weight information, it does not include the weight of the shell. All right, and this is important when we're filling our capsules. If the medication, like the dose, is not enough to fill the shell, we normally add diluent to help fill the remaining space. The actual space inside the capsule needs to be occupied by the powder or in manufacturing cases, granules. And so it's important to pay attention to the size and the volume and make sure your capsules are elegantly filled. So in this series of recording, you'll be introduced to the displacement method, where we use the fill capacity information, and we also have the fill volume information. So let's look at our capsule. Here we have some pictures. Clearly you can see the head, and this is the body. Now, the body is what we will pack the powder in, and then we snap on the cap. There's a lock ring that once you securely shut your capsules, they are permanently sealed. So a capsule has a body and a cap. When we talk about the fill capacity for a capsule, it's the body that is filled with the powder. It's important to know the density information for the powder if you're doing the density calculation. If not, you need to know the fill weight for your capsule for the powder. Now, when we are doing capsule compounding, the minimum recommended weight, the powder to at least fill a capsule, is 100 milligram, which is, I think, is a class 2 prescription balance, because the class A balance is 120 milligrams. That's the least weighable quantity. This little snippet of notes was taken from the pharmaceutical technology book, and I just wanted to read it for you so you have an appreciation from different resources. The fill capacity, which is a powder that fills a shell, is dependent on the physical size of the capsule. Again, capsules come in different size. It also is dependent on the type of formulation. Think about it carefully. Some powders have different shape, crystalline, circular, needle-like shape. The particles different. And the bulkiness, the air pockets between the powder bed is also different. We talk about the void and the porosity of a powder bed. So when you combine the different uniqueness of a powder, you're going to see how that plays out, where the fill capacity can vary for different powders for a given capsule. Now, the equation density is equal to mass over volume plays out when we are trying to solve for the mass of the powder that fills a capsule shell. So once we multiply the density of the powder times the volume of the shell, you can actually find the fill capacity. Let's look at this resource, Capsule Connection, right? They showed us their table, and it's really beautiful when you look at how it plays out. So they have 000 size capsule shell. So we're going to read across. The size is 000 0 0 0 0 0 1 2 3 4. 4 being the smallest, while the 000 is the largest of the capsule. Let's look at the difference. The capacity. This is 1.37 mil in capacity, but a size 4 shell is 0.21. Very small capacity. But let's look at it. For a powder with a given density, let's see how the equation plays out. The very first powder, the density is 0.6 gram per mil. How do you think they got this 822 milligram for the fill capacity? Density is equal to mass over volume. So if you want to find the mass, the density of the powder, 0.6, times the capacity of the shell, 1.37, and that's how you actually solve the 822 milligram. You can feel free to play with the equation and arrive these remaining information. And all we used was the volume of the shell and the different densities of the powder. This is why I say to you that whenever you have a question, whether it's the volume of the powder that's given or the fill capacity, using the equation density is equal to mass over volume, you can interchange between both versions of the calculation. Now, this chart is taken from your textbook on page 338, where we can have an appreciation for different size capsule shell. The largest is 000, and the smallest in this table is 5, unlike the previous video where the website stopped at 4. The 1.4 mil, you can see, is the largest of the lot, and then the smaller shell is 0.13 in terms of mil. But let's look at lactose. So lactose is an example. When they filled the body, remember the cap doesn't take place in the filling. The cap just closes the shell to secure the powder. So when the body is nicely filled with powder, This is the milligram capacity. But let's look at it now. Different drugs have different behavior. So if we look at a size 5 capsule shell, a powder that is 65 milligram up to 130 milligram range can fit in a size 5 capsule. Let's look at a 4. Powder from 100 milligram to 260 milligram can fit in a size 4. For size 3, from 120 milligram up to 390 milligram can go into a size 3. So the range again is there because drug A may have a different shape and porosity or bulkiness from powder B, and each powder have their own characteristics. That is why when you're doing a capsule calculation, the density of the unique powder or the fill capacity of that unique powder is important to fill the shell. You cannot use the fill capacity for powder B for powder A. No, it will not fit in the capsule the same way. So let's look at it. The goal is to elegantly fill our capsule. Nice, not to stuff it like a stuffed turkey, nor to underfill it so it looks empty. So you want the capsule to be accurate with dosage, good bioavailability, which means it breaks down and dissolves nicely, easy to fill, easy to produce, stable, and very elegant. The body, again, is what we fill with the drug mixture, not the cap. The cap should fit nice and snugly over it to retain the contents, and you snap it shut. You actually feel that snapping when you're closing it together. So importantly for you, you develop your formulation, you select the appropriate size based on the fill capacity or the density of the powder, right? You fill your shells, you seal them, clean them, and polish them and send them for your patient. Again, this picture is very instructive. The powder is normally formed into a rectangular cake, which is called the punch method, and the body, using gloved hands, is punched into the powder bed. You seal you level off the tip of the powder so it's not into a peak, and you snap the cap on loosely initially. Dust it off, check the weight, and if it's a little bit under, you can feel free to pull off the cap and pack it properly. And once you finish and you verify the weight, which is the powder plus the shell, you seal it and send it off. Now, there are some important words as we wrap up this video that you need to appreciate. Triturates will come again when you're making capsules, because if a drug is, say, 10 milligrams and you're calculating for 5 capsules, that's 50 milligrams. That cannot be weighed. And so you also make a triturate or a dilution from which the required aliquot will be removed and carry the drug that you need. There is a video recording that caters to making capsules with triturate, and so I will not go in much detail with the calculation in this introductory video. Importantly, trituration is a loose word term which is used for the blending of powders, the mixing of powders, but in PharmCal, we also use it to refer to a dilution which has been made. So if you're reading any pharmaceutics book, you may see trituration being used in the context of the blending of powders. I just wanted to alert you to that. Now, when you prepare the capsules, it's important to recognize that the weight per capsule is the last step of the calculation, which is the API, whatever the API source is, whether it's a triturate, a pure powder, or a tablet powder, which is tablets crushed into powder form, plus the diluent. And to get the weight of the capsule, you have to add the weight of the shell. So whenever we give you the data table, you'd always see the weight of the empty shell in the information. Please review how to make triturates because it will come in making capsules and making charts. If the drug is less than 10 milligrams, a serial dilution is normally warranted. We do not give you serial dilution in assessments, but you need to be aware of what it is. Serial dilution simply means that one triturate is made from which an aliquot is removed, normally the least weighable, and that aliquot is the starter for another dilution, which is why it's called serial. You may do 3 dilutions, and that's why we call it a serial, depending on how small the drug that you want to make your capsules. So let's think of a scenario where the dose is 1 milligram and you're making 7 capsules. Then you need 7 milligrams of drug. You have to do a serial dilution to get the drug into a weighable form, because there's no balance that can actually weigh 7 milligrams. But what if the drug is 10 milligrams and up to half of the least weighable, say less than 60 milligrams, less than 60 milligrams. So you need 10 milligrams or 50 milligrams. Then you can use your aliquot method or your least weighable method to make your drug weighable. And once you've made your drug weighable, then you can proceed to your capsule calculation. Now, what if what you need is exactly half and greater than half of the least weighable? Then you'll do what we call a 1-in-2 dilution. And so these are really foundation concepts that can face you in charts or in capsules. There is a general rule that we're introducing you to, that if triturates are used to make capsules, if the concentration is less than 50%, right, then the aliquot is normally treated as though it is the diluent. Whichever diluent is used to make the triturate, the fill capacity of that in triturate. So if it's starch, then the fill weight of starch is what will be used in your calculation. So you do not need the fill capacity information really for a capsule if the triturate is less than 50%. If the triturate is greater than 50% or 50% and greater, then whatever drug is present in the aliquot, you will use the displacement data or the fill data or the density data to find out the starch which is represented by that drug, right? You add it to the starch present in the aliquot, and that's what you use in your capsule calculation. Now, for PharmCal, we will expose you to triturates less than 50% because it's the easier thing at this level. But for year 2 students, we do expose you to 50% and greater in making your capsules. And that brings us to the end of our first recording for key concepts in making capsules. Thank you for listening.